Yeah, hi, am I audible? Can you please just say?
Yeah, you're audible.
Yeah,
Go on.
okay. So I will wait for 2 more minutes, then we will start.
Okay.
Yeah, so let's begin. So, hello everyone, my name is Roya Mukherjee, and I am a PMRF research scholar at the Department of Computer Science and Engineering, IIT Kharagpur. So, I'll be taking this tutorial for NPTEL course on reinforcement learning. So, this session is being recorded. Also, we will be solving mostly last year questions, and like previous week, I will be giving you some demo on some codes on like how to do it and all, like this week's algorithms and all. So we will have a basic overview on everything that was covered in week two, mainly like the bounded problems, the bounds of UCP and PAC. So I will give you a brief introduction again of the topic, so that you get an idea of what was being taught, and just a wisdom revision. So also feel free to ask me any question whenever you want if you have any doubt regarding anything. Okay, so let's begin this week. So, so our topic of interest in this week has been three topics. One is UCB, another is PAC, another is Thomson sampling. So these both are they were given some proofs of how to find out the bounds and all for each of them. Yeah. So let me be honest. This week, it was a little bit difficult. So there were lots of theorems, lots of proofs, right? So for UCV, there was given some proofs of how to do it, and for PAC also there were given two. There are two PAC algorithms. One was knife PAC, and another was your median elimination PAC. So both in the course it was covered both derivation of how to come out to the bound. So the fundamental thing in both of the case was we were trying to minimize the regret, right? So we are trying to get a, not minimize the regret. We are trying to get a bound on the how much the regret can be before we are getting an optimal arm, right? So that was the main crux of it. So if you have any doubts regarding the solving of that, because I know it was a very tedious part, the entire solving portion, you can ask, or I can give you a basic crux of what was done regarding it. UCB, I guess everybody understand what was UCB. So upper confidence bound. So basically, what we have. So like we are doing a sampling. Like we are calculating the reward for, let's say, arm. Let's say A. So we are calculating the reward as Q of like A plus some confidence term, right? Some confidence term we are adding. So in previous week, what we have seen that there was initially we are doing a greedy epsilon greedy technique. So in epsilon greedy, it was what our time that epsilon times we are taking the one which is the most optimal which we have found, and 1 minus 1 epsilon time what we are doing, we are just exploration. So we are choosing randomly some other one, right? So this one we did. So at each step we are taking the max, right? So for UCB, what we are trying to do, we are trying to get a bound of, okay, we are estimating a probability. We are estimating that this can be the value of Q, but we want a bound, like between this bound, that this value of Q will lie, right? So that C term was given us this exploration part. So as and when the C part, as you are doing more and more number of sampling, we are coming to the term that, okay, this is the optimal Q that we need to select. So if I need to write down the term for that one, okay, so let me write it down. So QA is equal to, sorry, reward is Q star A is equals to QA plus 2 ln at time t, that means at time t step, Q star t time t plus nj. So where nj is the number of times we have taken this arm j. So in a we can write number of times we have selected arm A. So so initially this value will be very large, right? When only one time we have selected. So the basic algorithm goes like this, right? So every time, uh, so so when we are previous week another concept will come out, that initial value, right? So when we are so we saw that if you are getting the initial value as high, suppose initially, so in epsilon greedy we are taking the q value to be always 0, initial q value to be always 0. So what we found is that if the initial q value is, if you keep it at some high value like 10, what will happen is that each arm will get selected at least once. So that UCB also like does the same thing, like each arm gets selected at max once. So let us say that there are k arms, and each arm gets selected at least once, right? So if you are selecting the arm only one, so what will be this value will be very high, right? So 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 uh, so that doesn't give us the much of the confidence. So our target will be to get this value reduced. For the optimal one, this value should be very low. Why it will be low? Because as this denominator value goes up, as the number of time j has been selected, or suppose a has been selected, goes up, that means this confidence, this bound, the confidence will go low. So if initially, if this is our optimal j and we are saying that this is the bound initially when we are initializing it, so as and when we sample mode, this bound will get smaller. we can say more confidently that yes, the optimal value rise for this arm lies somewhere between this value, whereas initially we are saying that the optimal value lies somewhere here, right? So as and when as we do more and more sampling, like sampling in the sense, so you understand what is sampling, right? Sampling is in the sense you are running the bandit arm more than once, like you are continuously applying the running that arm, right? So that is what you mean by sampling. So this is the basic concept of UCB. So as you do more sampling, the confidence interval will more and more get smaller, and this one indicates the confidence interval. This term indicates the, so does the confidence interval, right? Now you can also think about that as you are as we are doing more and more sampling, the we are reducing the basically the regret. So if the value was initially high, that means the regret was very high. Now as we do more and more sampling, the regret is getting smaller and smaller, right? So let me show you a specific code for this UCB. So before showing you the UCB, I wanted to show you this one. So effect of initial value on stationary bandit problems. So what is the effect on when we set the bandit like the initial value to a little bit higher than expected? So let me run this code. So first we are, so initially so in our previous problems, when last week when I discussed, so the initial values were always all initialized to 0. So now we are saying that we are okay, so the initial q values will be plus 5. So initial reward, let's say it is already 5, and then it will basically gradually uh, simulate and go to your optimal value. Okay, so this, let's run this code. So so let me show you where we have made a change. So here we are taking a initial value as an input. So if we give it as 0, the reward estimates, initial reward estimates will be 0. If we give it a value 1, the initial reward estimates will be 1. Or some, if it is 5, then the initial reward estimates will be 5. So that we are doing, and we are taken a step size at 0.1, just like previous example we have taken last time. Now that is the only change. So like if previously we are so if you are taking as the greedy experiment, so we have taken the epsilon here also. So here we have taken the epsilon, and we are done the same thing, that where we are estimating and picking the algorithm, like we are just taking the max if it is greater than epsilon and dot. That is the basic thing which we did last time. Here is your q equation, that qn is equal to qn plus step size into r minus qn, right? And we are running this for in bandit. So bandit is the number of experiments we are doing. Okay, so we run this code. Okay, so now we are initializing the bandit, that we are, it is a 10 bandit 10 lever problem, like 10 arm bandit, and there are 20,000 experiments we are doing on it. Now let's run this code. Okay, so we have epsilon values 0 and 0.1, and we have initial values 5 and 0. So there are two. So epsilon value 0, 5, it is like one plot. Another plot is epsilon value 0.1 and the initial value is 0. So we'll now check which one gives us the best value. Okay. So any doubt so far regarding UCB? So let this code be running. So any doubt regarding so far this UCB and all? So you need to understand first what is UCB. Then we'll cover how the bounds and all are happening. So have you gone through the paper? I mean, it is a little bit like this part of the like portion on the syllabus is not on the books. You have to read the paper. So any doubt you can ask regarding it. Not yet. Yeah, planning to soon. Yeah. So I have like previously gone through the paper and I have seen that you don't have to read the whole paper. You just need to read 1 or 2 pages. Okay. What I will suggest is that you follow the lectures. You take a printout of that paper and whatever notations that is using. So you just copy it down in the paper and it will very simplify for you to understand. Let's say this time. So you lot have understood the.
Sir, please share the title of that paper, title and author of the paper.
Okay. I have with me, so I am sending it. Yeah. So this is one paper, finite analysis of multi-arm bandit problem by Peter Orr. Another is this one. Okay, these are the two papers from where the derivations were done basically. Okay, so now the results have arrived. Let's see. Okay, so notice this is our the blue one is the one where initial value was 5. So initial value 5 and epsilon is 0. So notice initially it did some exploration, right? The value started like it thought, okay, now we have seen the optimal action we have picked up. Okay, so it did some exploring and then it give you the better optimal action per second over time. Whereas if you look at the epsilon dt output, so initial value was 0 and the epsilon was 0.1, it just went like that. So even though initially it was giving a better result than your uh, like initial value problem, but over time the initial optimistic value give you a better result than your epsilon reward. So that's the crux of this like that shows that uh, this this is your that initial value gives you a better result than your normal epsilon values. Okay, so initially if you have taken a very high reward, like okay, that you assume it is 5, sometimes it will give you an optimal result for few minutes, then it will start exploring, and when it starts exploring it gives you a overall better result. So you would see with theory parts, this kind of give it a gist of it. Yeah, so what UCB does is basically this. Okay, let me share it now. So okay, so UCB has two parts. So what was taught in the class this week was deriving your bounds between the like what is the bound of your max regret. Okay, so but the crux of UCB is this portion, right? So at any time step t, so suppose you are selecting a arm A, and suppose this is your q star A. Okay, So what so what our UCB says is that you have your, okay, you have your Q algorithm that previously you have done, but along with I'm adding a confidence part. Okay, so suppose this is your initial estimate. So this is your initial estimate, and you are saying, when suppose you have sampled it from say NA equals to 1, that you have sampled the A for only one term. So that time your confidence interval was this big, right? So over time, as and when you do a much better sampling, your interval will ultimately come down to this, as and when you are doing more and more sampling for any harm. Okay, so as you do more sampling, you can say that with more confidence that this is the interval in which your Q star value is present. Okay, so that is mainly what UCB does. So this week there was like, well, the proof of UCB was to find the bound of the regret, right? I will explain it through the, like, I will go a little bit through it when I am explaining the exercises, but I'm not going to do the full proof again because it will take a lot of time. Okay, uh, so so as I was explaining, this was the initial optimistic initial value problem. Okay, so mm, similarly, if we choose this, so now we have both have epsilon. Okay, so both are having is an epsilon greedy, and the initial value of one is 0, another one is 5. Then also you see, uh, with a initial value we are getting a much bigger optimal action over time as the steps increases. Okay, okay. Now if we do another experiment, so this is the final experiment which I did, was that these codes are same, we are just changing the values, nothing more. The code is almost same. So in this experiment what we did, we take three different initial values. So one we take is 5, another is -5, another is 10. So for the -5, that is the green one, you see it fall flat, like it doesn't do anything, it cannot get the optimal value at all. But you see, for 0 it was always there, but for 5 and 10 there are two different outcomes. So while 10 does much more exploration and ultimately reaches the same optimal value, but you see the regret is much high. What how do you, so given a graph, how do you calculate the regret? We did it last time, right? So you take like the area of the curve under y-axis, like the y under y-axis, you take the area of the curve, right? So that gives you the regret. So if you look at this graph, which one will have a greater regret, black or blue? So if we take the area under y-axis, so which one will give you the more regret if we do take the area under y-axis? So obviously the black one will give you more area under if you take the area under y-axis. So so obviously, so like higher initial estimate is also not a good option. Is a great idea, right? So the best option is for you will be to select a optimal value which is not a big high or a too bit low. So in this experiment, 5 is your best bet. So one way you can do it for any random problem which you are given, that you do some experiments, because this won't take much time. So you have to run it for 1,000 steps and all, and then you can get the a good initial optimistic value to how much it should be done. Okay, so this one was your optimal optimistic initial value problem. Okay. Now we'll come to UCB. Now I will show you an UCB code. Okay. So this is your this is your equation, right? For at any time t, you select the arm which has the maximum qt plus a qta plus c ln t nt by a, right? This is the one you select every iteration, right? So let's look at the code and what we have done different this time. So this is your code UCBC. So you are taking an initial value and a confidence, right? So here C is your confidence. So the same way you are doing the estimating the rewards. So you are taking initial value and multiplying it with something, some 10. Now what you are doing, you are like, where is your confidence? Okay, so here you are doing this UCB reward estimation. So estimated reward for problem this, action count this and this. Okay, so this expression estimate reward estimate is basically your QAT. This is your confidence C, and then this is the term here C ln T and divided by NTA, right? Right, so this is how you are updating your UCB and you are choosing an action based on the UCB. And here you are doing the previously what you are doing, that increment and update those part. So let me run it. Test bed we are initializing. This is our UCB code. And now this is our UCB values 2, 5 and 0. So let's run it. Are there any literature which explain the UCB algorithms, or the papers are the better one? UCB like so that Barton book has UCB explained quite easily, right? So the UCB part is there, but what it doesn't have is your what it doesn't have is that bound explanation, that theorem derivation and all. So for that you need to read the paper, but the paper is very difficult to read. Okay, so what I will suggest is download the paper, take a printout, and when you follow the lecture and how they are doing the lecture, you try to match it with the paper, how it is done. Okay, so in paper they are doing a lot of many step jumps and all, so that is very difficult to follow. And the paper, not every part of the paper is in the syllabus which sir has done. So only the one theorem sir has proved. There are many more theorems there. Okay, so the result has arrived. So this is your. So you see, this is with confidence C you are getting this output, and when the confidence is 0 you are getting this output. Whereas when the confidence is 5, while you are getting initially a good response, over time the reward is not good, right? So that explains like how you have to vary your parameters in the UCB to get a good result, right? So a C value of 2 is getting you a better result than C value of 5. Whereas C value of 0, that means if you are doing a C value of 0, that is basically you are killing this part. So you are killing this part. So basically you are killing this part of the of your equation, and you are basically doing a greedy algorithm, nothing more. So at each step you are taking the max. So that is your quite a good example of how the c values and other values are selected, and what you can select to get a good output. Similarly, we have done something called, yeah, so confidence of 2 and epsilon 0.1. This is the output you will get. So epsilon 0.1, you mean this red one is means this epsilon greedy output, and this is your UCB output. Again you see UCB outperforms your epsilon greedy algorithm quite easily. That is what this part means. So any more doubt regarding your UCB and all? Next, like, so I hope you got this equation that gives the expected regret after any number. So this equation, it was given in the class. Uh, so 8 ln ln by delta I plus 1 plus pi square 3. Right, you got this output, right? This was shown in your class, right? For any ti of n, where I is a particular arm and n is the number of steps, right? So this entire proof was shown how to calculate it from like to dividing it into parts and all. So I will not go through it again. So the other thing that was shown was this pack bounds with alpha and sigma. So what is alpha and what is sigma in pack bound? Sorry, not sigma, delta. So what does this sigma and delta means? So what does pack means? So in previously what you are selecting is argmax QA, right? So here instead of so so here what we are doing, so instead of taking directly QA, we are taking the probability of selecting of that arm being the having the highest QA, right? So here you are doing basically the probability instead of taking directly our values, right? In pack bounds. So the what does epsilon and sigma means for pack bound? So while in UCB you are having a interval, so if this one it was your Q and there were a interval between that, here it is little bit different. Here you are saying, okay, this may be your optimal arm and optimal output Q star A. You are saying that, okay, I will be selecting an arm with with reward, expected reward QA I QA, such that it is epsilon away from the correct value. So you are saying that whatever you are expecting is epsilon away from this correct value. So whatever arm you are picking, you are saying that you are not picking up the best arm, but whatever arm you are picking, which is in that distributions epsilon away from the best one, right? And you are saying that the probability of that picking up is 1 by delta. So you are 1 by delta with 1 by delta probability, you are sure that whatever arm you are picking, its reward is epsilon away from the like the perfect one, the optimal one, right? That is what this two term sigma and delta says. Then you are introduced to two pack bounds. One was your knife, and another was your median. So what was you're doing in knife? You're giving a fixed value, and each time you sample the each arm that amount of time, and after that you pick the one with the max probability. That was your knife pack bound, right? So there was a particular value that was provided, so with that L and something. So for each arm you pull that amount of time, and after that the one which has the highest probability you take that one. That was your knife pack bound. Other one was your median median elimination. So in that case, what you are doing, at each round you are calculating the probability, right? By picking up n number, some x number of times you are drawing the arm, and at each round you are selecting the median probability. At the median probability, so the one in the lower half of the median, you are just eliminating that, and you are taking the one which is higher probability, right? So that's why at each run you are eliminating one after the another the pack your arms, okay? And you continue that experiment as long as you don't get the number of one arms remaining is only one. So that one was your that that one was your median elimination. So if I have to say the median elimination again, so you are drawing an arm, then draw an arm, suppose sometimes, like let's say x number of times, calculate the probability. Now calculate the median for each round. For each round, for each arm, so you calculate the probability for each for all arms. Calculate the median of all arms and eliminate half of them, right, lower half. And you repeat it until one arm is present. So that is your optimal arm, right? That is your median elimination pack algorithm, right? There are basically now it's quite interesting. Both all may or may not give your best optimal output, but whatever output you are generating, it is sigma times close to the optimal one, and you can say that with confidence, 1 minus delta probability, right? So any doubt regarding pack mounts? So pack, if you like in the book, pack is not mentioned, but basically is that gradient found is basically the pack there. So that gives a small idea of your how your probability based sampling is done. Okay. So last topic that was discussed this week was your Thompson sampling. So what Thompson sampling did was, so suppose there you have been given many different distributions for each arm. So let's say this is arm 1, arm 2, arm 3 and arm 4. So you have, these are your rewards, right? And they are given different type of sampling. So how, so what, when you're doing sampling, what is your target? Your target is to pick the best arm, right? Sampling, what do you mean by sampling, right? Like if you're doing a probability of suppose you you have been given a task that you toss a coin until and unless you get 4 heads consecutively. So that is your sampling, right? You go on tossing the coin and all. So that is your sampling. Okay. So in Thompson sampling, so in previous algorithms like in PAC, what you are doing, so you are probing each arm, like what we call is sampling each arm some n number of times, and you calculate the probability of your of that arm being the maximum, of that arm being the optimal one, right? And then you select that one. So here what you are doing, you select a random, you select a random points in each of these different distribution, and you create your own distribution, and then you perform your bandit algorithms. So that is your Thompson sampling, nothing more, nothing extraordinary, but there are many objectives fulfilled using this. Okay, so let's come now to the problems for this week. So this is your question one. So we have the following statement is not true about Thompson sampling or posterior sampling, right? Which of the following statements is not true? So after each sample is drawn, option A, the Q star distribution of that sampled arm is updated to the true distribution. Do we need to do that? Yes, we do that. So after each sampling, we basically choose a value here and we try to update it closer to the true distribution. So basically, each arm has its own distribution. We want to find a optimal distribution based on out of it. So that is the objective. So this one is your first option is your true. Thomson sampling has shown to generally give better regret bound than UCB. So if you read about Thomson sampling, this has been shown to give better bounds than UCB. So like the bounds that UCB was giving for output for a reward QA. So Thomson sampling generally gives you better regret bound than UCB. What about option C? In Thomson sampling, we do not need to eliminate arms each round to get a good sample. So true. So that is the that is the our that is what you need for pack. For Thomson, you don't need to eliminate arms. So we don't need to eliminate arms. So eliminate arm is for your pack. And about option D, so algorithm requires that we use Gaussian priors to represent distribution about keystone. So this one is false because Thomson sampling doesn't bound you bound you to a particular distribution. Anything is preferred. So option D is not true. Okay. So any doubt? Okay, so let's come to this one. So the UCB, the term 2n minus L is added to each arm's Q, and the arm with the highest value of this sum is chosen, right? The arm with the highest value of this sum is chosen. So which of the following would be definitely happen to the frequency of picking suboptimal arms when adding this instead of this? So let's look at this. So this was initially our term 2ln n divided by nj. Suppose nj is suboptimal. Okay, so what will happen to this value? If suppose nj is suboptimal, let's look at the uh, original value, the original port. We will change it later. So suppose nj is suboptimal, what will happen in that case? So let me just write it j. So if we sample j more, what will happen? If we sample j more, we will so basically you have this qj term with it. Okay.
In confidence bound will come down.
uh, Confidence bound will come down. True.
J increases.
Yeah. So if we so think about this way, if we don't have the argmax and you are trying to compute this only this arm only total every time, so this j value will increase, but the qj value, we will come to know that this is not the correct one. The qj value will not be close to your q star j, the q star a, the one that you require, the optimal one. Suppose if q star a is your best one, so if you sample it more, what will happen? So you will gradually come to know that qj is not your best option. So if you are doing it randomly, what will happen? You will generally come to know that this is not the good one, and over time you will not choose it more, right? So over time, when your bound decreases, you will not choose it more, because you know now that this qj is very far from q star, is very far from q star. It is not optimal. Okay. Okay. So if you sample more, the qj will be chosen less, more and more less, because you will come to understand that this is not the good one. Now if j is optimal, let's say it is optimal, right? So if after few rounds, if you come to know this is optimal, so gradually it will choose itself more, right? So it will be chosen more, right? So ultimately it comes down to this, that this value of nj, it doesn't matter how many times you are chosen. Ultimately it will depend whether the j is optimal or not. So it doesn't matter whether you change the value of nj to nj square or nj cube. What matter is it will be chosen more or less frequently based on whether it is optimal or suboptimal, right? So in that sense, one thing one thing will happen. So if you are increasing this value, so from nj to nj square, so obviously your denominator gets reduced. So obviously your denominator gets reduced. So what we can say is, we will get the bounds decreased more fast. Will decrease the bound faster. Let's say it will the bounds will get decreased faster, right? So so this nj determines whether the bound will get decreased faster or not, but it doesn't determine whether the suboptimal arm will be chosen more frequently or less frequently. That depends on your sampling. So if you are doing more sampling, then it could be chosen less, because you will come to know that is optimal or suboptimal. Or you are doing less sampling, then it will suboptimal charms will be chosen more frequently, because okay, you have done less sampling, right? So the correct option in that case is option D, right? Because by increasing the number of sampling, what you are doing is you are increasing your confidence of knowing whether this is your optimal or not. So suboptimal arms will be chosen or not chosen will completely depend about the number of sampling we are doing for that j. It doesn't depend whether j value increases or not. So any doubt regarding this? Also, is this a good way to do it? So your question will be that, so if you can do it nj square nj cube, so why it is not done? Why it is not done? Because if you are sampling it more, so let's say you do 16 sampling, right? For nj equals to 16, for this denominator to reach 16, so let's say, so this value say, let's say nj equals to 16, right? But with nj square, that means for nj equals to 4, let's say this is k, suppose nk square, let's say nk equals to 4. So 4, so by 4, only 4 sampling you are doing this, whereas for 16 sampling you are doing this, right? So by observing very less, by doing very less sampling, you are trying to reach your try to tell more confidently that okay, this bound is good or bad, which is not always the good option to do it, right? So you may find out that only by 16 sampling, by only by 4 sampling I have reduced it, but whatever you have reduced is not the may not be the good reduction, may not be the confidence which you have gained is not maybe right. There may be any fallacy in your assumption. So so it is not optimal to just randomly squaring the number of samplings. Okay. Okay, so let's go to the next one. So in the proof of UCB theorem, when L is equals to 8 Lm by sigma I square, Q star A star minus Q star I minus 2 CLM is equals to 0. Yeah, true. Which of the following correctly explains q star a star minus q star I minus 2 cm TISI being less than 0 when we replace the fixed value of L by TISI number of times the arm I is selected. Note CLM is basically this, and q star I star I equals to delta I. So, okay, let's revisit that theorem once, proof of the theorem once. So that will help. Let me write few. Let me write few updated. Uh, yeah. So let me write few statements. So, you are given q star a star minus q star I is less than q star I. So this is saying that q star a star minus q star I minus 2 cm TISI is less than 0. So we can rewrite it as q star a star is less than q star I plus 2 cm comma TISI, right? So this term you understand, right? This confidence is basically, so you have drawn m samples where and L is your number of times. Suppose this is for I, so let's say for L has been drawn n times. For I has been drawn n times. I has been drawn L times, right? So what they are saying is, so if which of the following describes, explain this. So suppose this is less than 0, so this is less than 0, that means q star A is less than q star I plus 2 ci ti si. Okay, when we replace the fixed value of L, so we are replacing the fixed value of L. So what we have seen for the fixed value of L is that q star A star is equal to q star I is equals to q star I plus uh, plus your, for I equals to L we have got 2, we have got 1 minute, for L equals to L equals to q star A star minus q star I So what we did is we substituted this L value here, and you will get delta I. Now if you observe this value is delta I, right? The difference between your uh, optimal one versus the one which you have got for arm I, right? So this is your delta I. So this term is basically 0. So what we are now saying is that, so if instead of selecting L, we are selecting something, we are replacing it by the fixed value of TISI. So how many number of times the arm has been selected? So how many number of times you think the arm has been selected? So if you write this like this, Q star A star minus Q star I is less than 2 cm TISI, right? So this is your basically delta I. So that means 2 cm 2 cm L is less than this, or cm of L is less than cm of TISI. So what does that mean? That your confidence of CML is less than, like this concentration bound is less than this. What does that mean? What does this mean? So our objective is so if you look at this, so this means this one is correct, right? So this one is one correct, and there is, yes, this one is the only one correct, right? So what we are meaning is that our confidence on TI, so confidence bound on TISI is greater than confidence bound on L. Now also you need to notice L is the optimal one. So always this confidence bound should be the lowest, right? So that means TISI, like I has been selected, arm has been selected less than that of L, less than that of L. Because you see, if arm I has been selected L number of times, then the confidence bound will be same, but the confidence bound here is greater. So this will be the correct answer. TISI is less than L. I know this is one is little bit complicated. For that you need to go back to that proof. But essentially what the proof says is that for L value this will be this term will basically be this term will equal to this, so that is why it will be 0. So for the optimal one, so L gives you the optimal one, okay? So the optimal one's confidence, we can say with more confidence that this one is the optimal, right? Now when you are doing it for L, we have optimal, for L we have optimal. That means what? Anything less than L, so for any value less than L, we know it is suboptimal. It is suboptimal. What does that mean? That means its confidence bound is much more. So its confidence bound will be much more. So TISI's confidence bound will be much more. So that shows that TISI is basically less than L. So that is the reason we are not able to we are not able to we are not able to say that this confidence is greater than this. Ultimately, it boils down to the fact that this value is less than 0. Okay. So any doubt regarding this you can ask. This is little bit critical. Like I know that this is difficult to understand it. So as a postscript, I will say one thing. As we do more sampling, our confidence bound decreases, which we can say if it is optimal, we can say with more confidence it's optimal. Else, if it is non-optimal, we can say it is not. So basically, as you do more and more sampling, you come to terms whether it is an optimal one or a non-optimal one. Okay. Okay, so let's come to the next one. So, which of the following is true about median elimination algorithm? It is a regret minimizing algorithm. It is the probability of epsilon L optimal arms of round L being eliminated. Let's come to the first point. Is it median elimination algorithm? It is a regret minimization algorithm. Is it a regret minimization algorithm? So the answer is no.
No, it is not.
No. So so what we are doing in basically median algorithm elimination algorithm is that we are basically trying to get a confidence bound on optimal arm. We are not trying to reduce the regret. We are not trying to reduce the regret. We are trying to find a bound of the epsilon, right? So we are trying to find a bound on epsilon with 1 minus delta confidence, right? So this one is false. So option B, the probability epsilon L arms optimal arms of round L being eliminated is less than delta L for the round. So what it is saying is, suppose this is the probability that epsilon L optimal arms are eliminated at round L is less than delta L. Is this one correct or false? Is this one true or false? So, so you need to you need to look at the proof again, how we are doing. So at each round, what we are doing at median elimination, we are eliminating some arms and we are keeping some optimal arms. What the fun part is, if you negate this, so let's say negate this, you're just negating this. Okay. So what it will be? Probability that epsilon L optimal arms are selected at round L is greater than equals to 1 minus sigma, right? But this defines the median elimination algorithm, right? That at round L we are basically selecting epsilon L optimal arms, and the probability of selecting it is delta L. Sorry, delta is delta 1 minus delta L, right? So this one is correct, right? So what this means is this is basically an opposite of this. So this one is true, right? Because our definition of median elimination algorithm says that at each round we are selecting epsilon optimal arms with a probability 1 minus delta L. That is what your median elimination algorithm specifies. Right. So it is guaranteed to provide an optimal epsilon optimal arm at the end. Is it guaranteed that it will give us a optimal epsilon optimal arm at the end? No, we cannot guarantee it. False. All we are giving a probability, that is 1 minus delta at the end, right? We are giving you a probability that this might be an optimal arm. This might be an epsilon optimal arm. We are not guaranteeing you. We are giving a estimation. Probability, not estimation. Sorry. So last one, replacing epsilon with epsilon by 2 doubles the sample complexity. The sampling complexity depends on epsilon by 2. What is the sampling complexity of median elimination algorithm? What is the sample complexity? Let me write it down once. So sample complexity is equal to n epsilon square log 1 by delta, right? So they are saying is we are replacing epsilon with epsilon square. We are replacing epsilon by epsilon square. Does it increase the sample complexity? Does it increase it? So in hindsight, if you are doing it, so you will say that it will become n epsilon 4 epsilon square 4 log 1 by delta. So you are not doubling it, you are basically quadrupling it. So it's false, right? So the correct option is option B, right? So it was fun, like you need to remember in these cases the basic definition of uh, alpha comma delta, like median elimination algorithm for pack, nothing more. Okay, so let's go to the next one. So suppose, so we need 8 rounds of, so this is the question, 8 rounds of median elimination algorithm, median elimination to get a sigma delta pack. Approximately how many samples would have been required using naive pack algorithm given sigma and delta as this? Okay, so we have been told that 8 rounds of median elimination, right? Algo. So if you are doing 8 rounds of median elimination algorithm, so how many arms were there? So our question is, first, how many arms? So if you have noticed in the median elimination algorithm, so at each round, we are decreasing, we are uh, decreasing the number of arms by 2. So we are basically halving the total number of arms we have. So the simple formula is log number of arms is equals to number of rounds, log base 2, sorry, or number of arms is equals to 2 into number of rounds. So that is 2 to the power of 8, that is 256, right? So we get number of arms from this. So any doubt regarding this? Now we need to find out how many samples would have been required using knife. So number of samples in knife, number of samples L is equals to 4 epsilon square ln 2 into number of arms by delta. So that becomes 4 epsilon is basically your uh, half. Epsilon square half means 1 by 4. 4 goes up 16. 16 into ln 2k. So that is 2 into 256, and 1 divided by e is e. So that is so this is number of samples from 1 for 1 arm. Wait. Number of samples for knife is number of samples is equal to 2k epsilon 2k epsilon square ln 2k by delta. That is k is 256, 2 into 256. Epsilon square is basically 1 by 4 into ln 2 into 256 divided by 1 by e. Okay, so you need to calculate this one. So you need to calculate this one, and it will come down to ln e is so it will come down to
I think 14,824.
okay, yes, 14,824.
And 24.
So the correct answer will be 15,000. Okay, so like the main crux is that you need to remember this one, that number of arms is basically number of rounds is basically log of number of arms for median algorithm, median elimination. This is your number of sample drawing. So you can, if you want to remember, you can remember, but this is pretty straightforward result. The number of sampling you need to do. Okay. Okay, let's go to the next one. So consider the following equalities, inequalities for the UCB algorithm. So equalities, inequalities for the UCB algorithm. Following the notation in the lecture, TIN is the number of times the action I has been played in the previous n trials. CK, TAIK represent the confidence bound of I after k trials. Okay, fine. So here 4 equalities are given. We need to check all of them one by one. So let's look at the first one. It says Ti of n, so it says Ti of n is equals to 1 plus m equals to k plus 1 to n im is equals to I. So what does this represent? So what does this term mean? Each of them. If you have gone through the lecture, you know. So T of in is the number of times action I has been taken, played in the previous n trials. Okay. So if you understand, if you remember this UCB like bandit, so it specifies that each arm each arm is taken at least once. So arm I will value I will be played at least once. So that's why Ti is 1. Okay, so let's assume that for first k samples we draw one arm at a time, right? What does this mean? This means that we will select one, so this will have value 1 if I has been chosen at time m, else 0. So basically we are doing the counting. This is basically doing the counting, right? So this equation or equality is correct. This is correct. So 1 correct. Now let's look at number 2. Ti of n is equal to m equals to 1 to n, I of m of I. Is this equality correct? So this equality is also derived from the statement 1. So if you look at statement 1, it assumes already, so nothing to be assumed. So the algorithm says that all arms are at least picked at least once. So it says that okay, we will start counting. So we will not count the first k terms, we will start counting from k equals to 1. In this example, we are saying no, we will count from m equals to 1. So I will say that this one is also correct, because for I is equal m equals to 1 to k, Ti value will be 1, because it has been selected only once, and the rest is this part. So if we concentrate these two, this will come here, right? So this you can say as a superset of the previous equation, but the equality is same. So in both cases Ti value will remain same. So this one is also true. So number 2 correct. So any doubt regarding these two equations, you can just ask. Okay, so let's come to the next term. So here we are saying that Ti of n is less than equal to 1. So 1 is remaining same, is less than equal to 1 where we are saying q of m minus 1 a star plus tm minus 1 a star. So that is the optimal one at time m, optimal one at time m at step m minus 1 is less than equal to like the estimation of at I at time ti minus 1. Is this one correct? Is this inequality holds true? What does this equality says? So this says that we are only choosing I. We are only choosing I if its estimate is greater than current optimal, right? And that is why we will choose, right? So we choosing one arm is basically depends on certain criteria, right? It is not that we'll just go and randomly pick some arm. So it depends on the criteria that their estimation of its estimation of reward is more than the current optimal reward I am having, right? So this one is also correct because this is the only condition, only when we will pick up I, right? It is the only time we will pick up I, else not. But why the inequality? Why are not writing equal? Why are we not writing equal? So the one reason we are not writing equal because we don't know the estimation. So we are writing a confidence bound, right? So in some cases, since these are estimation, the estimation might be so there is a confidence bound in both. So q of m minus 1 I, and there is a confidence bound of, let's say this q m minus 1 a star, right? So we are we can assume that so in these ranges all of the values will be chosen, right? But if something in this range chosen, then it is not correct. We are our estimation is wrong, right? But these portions will always get selected. This portion will always get selected like it was in the case previously, right? Where our estimation was correct. But it is not that always our estimation will be correct. So the confidence bound may lead us to some failure path. So in that, so that's the scenario. So we are basically overcounting in this case. So with this bound, we are basically overcounting. So even though these two's output will already be present here, the value can be much more than that in such a case. So number 3 is also correct. Now let's come to number 4. What does number 4 tell us? Number 4 tell us is that we don't have any bound on A star. We are very confident that this one is our A star. We are very confident this one is A star. And we have some confidence issues with we have some bound regarding qm minus 1I, right? So again in this case, so this case is also correct if you look at it. So in this case we have just basically removed this part. So if you remove this part, if you look at this equation, so if this equation is correct, this equation also correct, because we are just removing this part. So this inequality will hold. If this inequality holds, this inequality also holds. What we are doing again in this case, we are overestimating it. We are overcounting, right? So this inequality also holds, right? So we gradually moved from one counting statement to another counting statement, and what we saw in its case is that these two are equal. These two are have no issues. But in this case, we are overcounting this part and we are bounding it with our UCB algorithm. We are UCB constants, right? And here also again we are again overcounting it with our UCB constants. So all of the three are correct. The option D is correct in this case. So any doubt regarding this? I mean, I understand that this one is a little bit trickier than previous, but if you have followed the algorithm that was like the derivation that was done in the class, this one you will get it easily, because there also we are doing all kinds of overcounting in each step. Okay, so let's look at the next one. So this one is saying that in case of UCB, the regret is generally of the form F1 plus C, for the confidence bound given by this, where Fn is this one and C is this one. Okay, fine. So this comes back from your uh, so this comes back from the derivation of the regret. So it's basically saying J is equals to 1 K 8 ln delta J plus 1 plus pi square 3 summation J equals to 1 to K delta J. What is the form of Fn for the confidence bound given by this? So you are saying we are replacing alpha with 2. We are replacing this 2 with alpha, where alpha value is greater than 2. So we are saying what will be this confidence value. Right. So what will be the problem here?
So is subdivision B is correct.
Mm-hmm. What?
And instead of alpha,
Mm-hmm.
uh, we are substituting. Sorry, instead of this
So instead of 2, we are substituting.
uh,
So 2
alpha
becomes here 2
greater
cube.
than
So you are saying alpha becomes alpha cube.
yes.
You are saying this is the answer. You are saying this one. Hmm. So where does this term comes in our derivation? So it comes at a point where you are choosing a random value of L, right? You are choosing a random value of L such that, uh, so let me just erase this one, clear the frame. Okay, so it comes back to our this equation, q star of, I mean, let me copy it here, I've done it before. Yeah, q star a star minus q star I is equals to, yeah, q star a star minus q star I is equals to 2 c of m comma l, right? C of 2 cm comma l, right? M was basically this value, right? Yeah, M was the top value. So I can remove that one here as n comma l, right? Which is basically 2 to the power of root 2 to the 2 into root alpha l of ln of that by nj. So ln of what was the value? The value was, the value was 8 ln n divided by sigma square. Okay, so I don't want to do it totally, but so if you look at this, what will happen here? So this one is your delta, delta I. So if you are squaring it, it will become delta I square. So what you will get? So so what you will get here is that if we get this one out, you will get 4 alpha. So you can do it, you can substitute these values and do it all. So it will come out to be this value, not a alpha cube. So you are basically here replacing these two with alpha. So this will come to be 4 alpha. Yeah, right. So you need to square this one and get it done with. So substituting the value and all will give you that. Okay. Okay. So let's now look at this one. So in a knife, alpha, alpha, gamma, alpha delta pack, we have, we draw this amount of samples to 2 sigma square ln k by delta for each arm instead of 2. So previously we were drawing this one 2 alpha square ln 2k by delta. Now we are doing only half, only half of that. So using the analysis presented in the lectures, what is the probability we guarantee that alpha arm return will have q star a close to v? So basically, what will be the value of delta? So here, so in original paper, what we are doing, we are getting uh, twice, right? So if it was delta, we are getting this. So what is the value of delta it will be? Suppose if it is delta 1, so what should be the value of delta? Suppose this is delta 2.
It's delta by 2.
Yeah, so it will be 2 by delta 1 is equals to 1 by delta 2, or delta 1 is equal to twice of delta 2. So the equation will become 1 minus 1 minus 2 delta, right? From initially, right? Or the opposite. Yeah, so this will be the answer. Okay, so let's come to this one. So here we have saying that we have a median elimination method for obtaining delta uh, epsilon delta back bounds. Now what will be the possible rule update for uh, sigma L and delta L if sigma 1 is equals to sigma by 3 and delta 1 is equal to delta by 4? So what will be the update rule? Like, so suppose you are given this, what will be the value chosen for L plus 1 and delta L plus 1, right? So so one thing you should know is that summation of L epsilon L should be less than equal to epsilon, like summation of all the epsilons over all the levels should be less than equals to epsilon, and summation of all delta over L should be less than equals to delta, right? Right. So how does this, so if you look at this equation, so how does how does the summation occur? So it will basically a GP series, right? So suppose this consider, so for epsilon 1 there are two values, 2 by 3 by 4 or 2 by 3. So let's say 3 by 4. So the first one will be 3 by 4 E1, then it will be 3 by 4 into 3 by 4 E2, right? E1, then it will be 3 by 4 into 3 by 4 into 3 by 4 E1. So this one is a GP series with the ratio 3 by 4. So first element is 3 by 4. So let's substitute this. So let's do the sum of the GP series. So S infinity, okay, in that case will be a by 1 minus r. A is epsilon 1 by 1 minus r. 1 minus r is 3 by 4. That is 4 epsilon 1. That value is 4 epsilon by 3. So we cannot take this update rule, because so the total sum is greater than epsilon. So epsilon 3 by 4 epsilon L for EL plus 1 is not correct, right? So the other option we have been given is 2 by 3. So let's do the sum for 2 by 3. 1 minus 1 by 2 by 3, that is 3 epsilon 1. Epsilon value is 3 by, epsilon by 3, so it will be 3 into 1 by 3, it will be epsilon. So that satisfies this bound. So epsilon's update rule will become epsilon L plus 1 is equals to 2 by 3 epsilon L, right? Similarly we need to do for delta. So if I consider delta 1 minus 4 by 5, we get 5 by 4, 5 delta, sorry, we get 5 delta. 5 delta is basically 5 by 4 delta. Total sum is 5 by 4 delta. 5 by 4 delta. Delta 1. Okay, so that is greater than, that doesn't hold this inequality. So that one is not correct. So the correct will be, so let's consider the next one. 1 minus uh, uh, delta 1 minus 1 by 3 by 4, that is 4 delta 1. 4 delta 1, delta 1 is 1 by 4, so it is 4 into 1 by 4 delta. So the total sum is less than equals to delta. In that case is equal less than equal to delta. So the correct answer is option 9C, right? So basically it is you have to you need to follow and consider these inequalities and check whether the summations are greater than or less than equal to 1. So you do a GP series. These are GP series sums, so you can do it. Okay. So let's come to the last one. Suppose you are facing a non-stationary bandit problem. We are to use posterior sampling for picking the correct term. Which is the likely change that needs to be done to the algorithm so that it update to the non-stationarity? So what does non-stationary bandit means? So non-stationary bandit, we have seen that we have an environment and we have your agent. So in a stationary bandit problem, the environment, stationary bandit problem, environment constant. Environment constant. And in a non-stationary, the environment can can update its distribution over time. So as a result, to adapt any algorithm to its non-stationarity, we need to update our bandit problems, our bandit agent, how you are sampling it. Like now, for our like posterior sampling, we don't have any step function. We don't have any step function, so that we can update it error and all. So what we can do is we can add some random noise to the probabilities so that it does some kind of exploration over time. Okay, so the correct answer is keep adding a slight noise to the posterior to prevent it from variance going down quickly. We need to add some noise over time. Okay, so that concludes this class, today's one. So hopefully you have understood it. So I will ask you to read those papers I mentioned in the chat, the two papers. So try to read those papers and follow the lectures again, so that will clear most of your concepts regarding this derivation and all. So if you have any question you can ask, else this is the end of the class. Thank you for joining.
Thank you, sir.
Yeah, so next week you can join again.